various delay constraints. Existence of broadcast advantage and node mobility bring about the possibility of reduced energy consumption, but also complicates the problem of minimal energy multicast. Previous works on this problem often focused on static networks or only studied the energy consumption at the transmitting side. Well, in this work, the authors focused on joint optimization of transmitting and receiving energy in delay-constrained mobile wireless networks. And here are two figures illustrate what is static multicast tree and what is mobile routing. The related works are two main parts. The first part includes work on minimal energy multicast problem. This problem is first proposed by Walther at 2001. Then in 2004, one gives NP harness and approximation algorithms. Moreover, there are some variants including delay constrained MEM, dotted circle where MEM with network coding and a distributed one in sensor networks. The second part is on performance trade-offs in mobile wireless networks, including delay and capacity trade-off, energy and delay trade-off, and resource and performance trade-off. However, there are some limitations. The both works only consider the energy consumed at the transmitting side, and the receiving energy is significant but more difficult to optimize due to its heterogeneity. In this paper, the authors investigated the problem of devising the transmission scheme with minimal energy consumption for delay-constrained mobile wireless networks. Here, energy consumption includes two parts, transmitting energy and receiving energy. And in this work, the authors gives approximation harness and a general optimization framework. Now let's come to the models and assumptions. Here, the models include three parts, network model, multicast model, and energy model. The first one is network model. In mobile or wireless networks with nodes feature mobility prediction, time being divided into slots. The mobile network is encoded as a sequence of graphs, G1, G2, and here, for example, G1 refers to the graph at time t, time slot t equals to 1. The graph at time t is denoted by this notation, where the notation Y denotes the node sets, ET denotes the H set, and WT denotes the weight function at time t. If an edge exists between node Vi and Vg, it will indicate that Vi can send message to Vg at time t using power larger than WT. Secondly, it is a multicast model. A transmission scheme consists of a sequence of tuples, and in each transmission, it includes parameters like this. Here, U denotes a sender, V denotes a set of receivers, and T is a time slot, P denotes the transmitting power. Furthermore, to make a feasible transmission scheme, the following three conditions should be satisfied. Firstly, the transmitting power P should be large enough to cover the set of receivers, and it should observe the Corel constraint. And thirdly, the data packet should reach all the multicast destinations within D time slots. And thirdly, the energy model. For a transmission turbo, the energy consumption of a transmission can be expressed like this. The energy consumption of the transmission scheme is the sum of all that in each transmission. And here here are two parameters. Here, P tau denotes the transmitting power, and F V tau denotes the receiving energy. The authors define a problem named as the delay-constrained minimum energy multicast problem. That is, given a mobile wireless networks, G1, G2 to GD, a source node S, a set T of destination nodes, and a delay constraint D. The goal is to find a feasible transmission scheme with minimal energy consumption. Okay, now let's come to the approximation harness. As this problem is combinatorial optimization problem, we first investigated its approximation harness. This is the theorem. This problem cannot be approximated within a factor better than 1/4 log k. Unless this expression, where k is a number of destinations. The proof is done by reduction from a second directed Steiner tree problem. And the reduction is an approximation preserving reduction, which allows us to draw a conclusion on approximation harness. Okay, now I will introduce the ConMap framework. It includes two cases. One is without receiving energy, and the other is the integration of receiving energy. Firstly, I will illustrate ConMap framework without considering receiving energy for clarity. There are three major steps. The first one is conversion into intermediate graph, and the third one is computation of Steiner tree. The third one is mapping into the transmission scheme. Let's see the first step. For each graph Gi, which denotes a network in time slot I, construct graph Li as follows. Firstly, create a vertex in Li for each node in GT, and it is named as original verticals. Then for the PU power levels of node U, add PU verticals into Li, and this is called power levels. Then add a directed edge from U to each of its power levels and set the weights as the transmitting power at the power level. And finally, add edges from power levels of each node to the original vertex that can be covered, like in this graph. Follow the chronological order. Add zero weight edges between original vertex that corresponds to the same node between adjacent layer. And the second step is computation of the Steiner tree. This problem is equivalent to the minimal detected Steiner tree problem in the intermediate graph, where the source is the original vertex that corresponds to the source node in L1, and the terminals are the original vertex that corresponds to the destination nodes in LD. This result can be proved by the construction and weights assignment of intermediate graph. After the conversation, existing algorithms for directed Steiner tree problem can be embedded into this framework. And here is the last step, mapping into the transmission scheme. And here is a lemma. Each feasible transmission scheme corresponds to a valid Steiner tree in the intermediate graph, and the energy consumption of the scheme equals to the cost of the corresponding Steiner tree. And then point the computed Steiner tree into canonical form and map the resulting tree back into a transmission scheme. The properties of ConMap are listed as below. This framework only incurs polynomial number of additional nodes, and it preserves the approximation ratio of the embedded Steiner tree algorithm, and it allows trade-off between performance and time complexity through applying different Steiner tree algorithms. And finally, the framework jointly optimizes transmitting and receiving energy, and it is suitable for a broad range of energy function. In this case, the authors considered receiving energy. The receiving energy of transmission can be modeled like this. Which depends on the number of intended receivers. And for the function f, it may be linear, sublinear, or superlinear to the number of intended receivers. In the linear case, ACKs are conducted without repeated transmission. And in sublinear case, mic layer has repeated a transmission but no ACK. And in superlinear case, there exists reliable mic layer transmission scheme with repeated transmission and ACKs. For linear receiving energy, the function f can be formulated like this. It is directly follows the ConMap framework without receiving energy by setting the weights of H's from power levels to original verticals as A instead of 0. And for nonlinear cases, the conversion to intermediate graph is similar as before, but it should replace power levels with more complicated gadgets that capture the receiving energy. And the computation of Steiner tree is the same as before. As for the second step, it requires additional procedure, and it can preserve the approximation ratio of the Steiner tree. Okay, now let's come to the experiments. The experiments are conducted based on 3 data sets. 2 of them are social networks, and the other is Roma taxi. The parameter setting is listed as below. For each data set, the authors exact 10 groups data of 15 nodes in 100 time slots and normalize the distance between nodes into the range of 10 to 5,000. Then the author set the delay constraint of the multicast session from 10 to 100 time slots. And they set the receiving energy function like this: Fk equals to 50k and the other 2. These 3 cases are designed for linear, sublinear, and superlinear cases, respectively. And there are algorithms embedded in ConMap. And here are experimental results. From the figures, we can see that when embedded with the aforementioned algorithms, ConMap achieves good performance and yields transmission scheme with small energy consumption, especially when we apply faster DSP that has good approximation guarantee. ConMap derives near optimal transmission scheme. And finally, the experimental results also show delay energy trade-off in mobile wireless network. And finally, the conclusion and future work. In this paper, the authors studied the problem of jointly optimizing multicast energy consumption in delay-constrained mobile wireless networks. And the authors first formulated their problem called DEMEM as a combinatorial optimization problem, and then proved its approximation hardness. And finally, they proposed a novel approximation framework, ConMap, for this problem, and evaluated its performance from both theoretical and impractical perspective. And The future work includes these two aspects. The authors have not taken into account the interference issue in wireless network. And the third one, it is interesting to investigate the influence of future mobility prediction on ConMap. That's all, thank you. And since I'm not the author of this paper, so if you have any questions, you can contact them by email. Thank you.